Hello everyone, good evening. Welcome to the solutions for BSDS sample paper 2024, and we are at question 24 itself. Question 24 is based on again differentiability. So you can see that we have a lot of questions relating to calculus and functions, limits, continuity, differentiability. So make sure to prepare this portion well. Right? If you need any help, do contact the number given in the comment section. We can help you from there. Alright, now back to the question. The set of real numbers at which the function f(x) equal to mod sin x plus mod cos x. Now I found a portion of this sum in a different problem given in the book, so I have taken that bit of solution from there. The rest of the part I will be working out with you. Alright, so let us understand what exact solution is given here. Now the solution here states that the set of real numbers, to find the set of numbers at which f(x) equal to sin x plus mod sin x plus mod cos is not differentiable, we have to analyze the behavior of the absolute value functions of mod sin x and mod cos x. Alright, so let us do them separately. So mod sin x and cos x are differentiable functions for all real numbers, right? They are continuous functions because you can draw them without lifting up your pen. Just draw the wavy function, it will be sin x, and draw another one out of phase, it will be cos x. Alright, but for mod of sin x, the non-differentiable points occur at all the roots of sin x equal to 0, right? Because the function does not get defined there. So it becomes a sharp turn. So where does non-differentiability occur? If the function has corners or if it changes directions abruptly. Now mod sin x will have a V shape at the roots. Alright, so what are the roots of sin x equal to 0? They are x equal to k pi. So we have to avoid these points. Similarly for mod cos x, the non-differentiable parts occur at cos x equal to 0, which are x equal to pi by 2 plus k pi. So if we just check the positive part, because the negative part will just be a reflection of these. So for the positive part, where will our points of non-differentiability lie? They will start from 0, then we have pi by 2, then pi, then 3 pi by 2, 2 pi, etc. Right? These come from these, the blue ones that I marked. They are the values x equal to k pi, and these values, the red ones that I am marking, these are the values of pi by 2 plus k pi, right? So the solution is basically a union of these, right? So it will be k pi x such that the differentiability criteria will be the union of these. K pi, k belongs to z, union pi by 2 plus k pi, k belongs to z. Now we don't see any options like this in the sum, right? So what do? We check the options to see which has all of the points as we require. Alright, so the first option, k pi by 2, that will give us all of the options, right? Because at k equal to 0, we will get 0. At k equal to 1, we will get pi by 2. At k equal to 2, we will get pi. Alright, so this entire series that we just described, we can write it out from these two itself. So the union will turn out to be k pi by 2, k belongs to z. I hope you could understand how we got the union. Right? We didn't do any set specific calculation, we just looked at the values that it might generate and then check the option which generates these values. So this is option A. Alright, now you could ask that, sir, why did you not take out the negative portion? The negative portion is completely symmetrical to the positive portion, right? Because if k goes from 0, 1, 2, 3, 4, you will get a sequence of pi's. And if k goes to the same things in the negative order, then you will get a similar sequence of pi's, but the signs will just be reversed. Alright, so I did not discuss the negative part. That doesn't mean that it is not there. It is there, it is just symmetric to the positive part. Okay, so I will be ending this question here. This was quite easy, and I'll see you in 25. Okay, question 25.